Welcome everyone, this is my first time doing a voiced video, so apologies in advance. And what I want to show here is a very simple 3D rendering technique known as the Raycasting. The minimal code that I will show is as simple as possible, needs no graphics libraries, it outputs in the text console and can be written in 15 minutes or so, and the link to the code will be added to the video description. The general idea of raycasting is as follows. We have a player and we cast a bunch of rays in some angle range that is equal to the field of view, and then we check where these rays intersect with walls. The longer the ray is, the larger is the distance to the wall, and so the height of the wall, as drawn on the screen, should be lower. Okay, so first thing we do is define some basic constants. The resolution is just the size of the screen in terms of characters. The normal console window is about 80 by 50, but everything below 200 or so is reasonable. Then we have the field of view, which is defined in the 0.1 degree increments. All angles in the code will be in 0.1 increments. I will show later why. Then there's the map size. We will have a very simple map, so 16 by 16 grid points is enough. Then a handy constant to convert the angles from degrees to radians. And finally, a table that contains values of sine function, because calculating sine function is a process that takes a lot of processing time, so it should be avoided if possible. And one of the simplest ways to optimize code is to pre-calculate everything that we can. Next we have some buffers that hold the output of an algorithm. First is the character buffer, which just holds all the characters that are on the screen. Then we have the list of the characters that we want to draw, from the darkest to the brightest. This could be improved or lengthened, and the output depends somewhat on what font are we using, but that's beside the point. Next is the height map, which just holds the height of the walls for every screen column. And finally the light map, which is brightness of the walls for every screen column. Finally we have the world map and then the player data. For this demonstration we only need three variables, the x and y coordinates and the angle. And the last variable is the position of the horizon. If we want to implement looking up down, then we simply move the horizon around. First we do some pre-calculation and we save the values of the sine function in the table. What noticing here is that we add a very small value to the angle, basically to avoid getting exact 90 degrees, 180 degrees and so on, because for these angles the sine function reaches 0 and then we get problems with the division by 0. And we can easily avoid that by simply adding a very small constant, which doesn't hurt the accuracy of our calculations. Then we calculate the correction time for the fisheye effect. This is just a cosine of the viewing angle. When standing near a straight wall, we can see that on the left the ray number 2 is longer than ray number 1. So logically, the part of the wall that is hit by ray number 2 should be a bit lower. But in fact, when we are standing beside a straight wall, we see a straight wall. That is because our brain is automatically correcting for this. Computer screen is not, so we have to do it manually. Then there's some simple stuff like adding borders on the edges of the map, then few random blocks inside, setting the player position, player angle and so on. Now the actual raycasting. we cast a ray for every single screen column, and the angle of the ray is the sum of the player angle and the position of the screen scaled by the field of view. Now we use our sine table to calculate the horizontal and vertical components of the ray velocity, and also the integer velocities that are used to jump between the grid points. This is basically all the math we have to use here. We have a ray going at some angle, and we use the sine and cosine function to separate the ray velocity into the horizontal and vertical components. When we get these components, we can update the ray coordinates by using these horizontal vertical velocities and time. The starting position of the ray is just the player position, and then we cast these positions to integers to get the map coordinates. And the starting distance is of course 0. In this implementation we are only checking for the intersections between the ray and the horizontal and vertical grid lines, so the maximum number of intersections possible is twice the map size. First things we do is to calculate the time needed for the ray to intersect the horizontal line and vertical line and find out which time is shorter. So we have some ray position that is a fractional number, and then we have a grid lines that are integer numbers. So by subtracting one from the other, we get the distance to the closest horizontal line and closest vertical line. When we have that distance, and we have the vertical and horizontal velocities, we can calculate time, and then we can choose whichever time is smaller, and that is our closest intersection. When we find the intersection, we can update the coordinates as needed and increment the traveled distance. So when the tracing ends, we don't need to calculate the distance manually, we have it already. We continue our tracing until we hit a wall, so a non-zero value of the map. And then all we have to do is to save some values. So first, we save the height of the wall, which is inversely proportional to the distance, and includes the fisheye correction term. Then we save the brightness. We can do all sorts of lights here, but the simplest one is just to have the north-south walls a bit brighter than the east-west, just like for example in Wolfenstein 3D game. And then we multiply this brightness by inverse of the height again, so the high walls that are close to us will be brighter. Now we have everything we need to draw the walls. We go column by column and fill them according to the height buffers and brightness buffers. Since our screen buffer is one-dimensional, we only need a single variable to keep track of where we are. We are going along a column, so to go one character down, we increment the offset by one whole row. And I have used a coordinate system where 0 is the middle of the screen and we go up or down by half the resolution. This is more handy in this case. And we are checking whether we are within the limits imposed by wall or outside of them, and then we either draw the wall or the floor and ceiling. For walls, we simply read the value for the light buffer. For floors and ceilings, we use a formula that is greater the closer we are to the screen edges. And we also add some dithering, which is a handy technique for low resolution and low amount of colors that makes the image a bit more fuzzy. And here we use very simple dithering technique that every second row and every second column is a bit brighter. Finally, we limit the character number to the number smaller than 10, because At the beginning, where we defined the character gradient, it was 10 characters long. This is especially important if we have multiple factors that affect the brightness. We can easily exceed the maximum brightness, and then we have to clamp the value down. Then we save the output in the character buffer. Finally, the last function that displays our character buffer on the screen, it simply outputs all the characters to the screen, nothing fancy here. And in the main function we use all our written functions, so we initialize, cast the rays, draw the walls, and then display this on the screen. This is how the program output should look like. If it's all messed up, then probably the window size is not set to the same value as the resolution defined in the program. The link to the code is added in the video description. I hope that this tutorial is useful, and thanks for watching.